All right, so today's webinar is focused on data uncertainty and design acceptance criteria. This is a webinar that's going to run for 1 hour, and it is an Ask the Experts webinar, which means that we have a panel of great experts here today on the topic who are ready and willing to answer your questions related to data uncertainty and design acceptance criteria. We're really glad to have you join us today, and we are looking forward to having a great session. So this webinar is brought to you by the Geotechnical Center of Excellence. We are housed within the School of Mining and Mineral Resources at the University of Arizona. We are an industry-funded and member-led center, and we work through practical geotechnical research and education to bridge gaps between academia, industry, and fields of study focused on geohazards in open pit and underground mining. We have a great team, and our team is supported by our members. If you are interested in learning more about our work, membership with the GCE, we'd be really happy to chat with you. Send us an email at gce@arizona.edu. And our panel today is coming from a course that's currently running through the GCE's professional development program. It is the Fundamentals of Open Pit Slope Design course, and it is currently available for registration. The panelists here today have contributed different modules on the topics in the course. Specifically, we are talking about the section on data uncertainty and design acceptance criteria today. But as you can see, there are many other topics that are covered within this the greater course that's shown here. As I mentioned, we are a member-led and supported organization. So I wanted to take a moment and just give some appreciation to those members that you see here on the screen. Without their support, we could not do all of the work that we do here at the GCE, and we really appreciate all of them. So thank you to our member companies. And the course that I mentioned was underwritten by the Large Open Pit Project, or the LOP. And it also is based on a textbook that was put out by the LOP called Guidelines for Open Pit Slope Design. If you're interested to learn more about the LOP or that textbook, you can go to lopproject.com. All right, now I would like to introduce the GCE webinar team who's here today to take your questions and help guide this conversation. So I am Jillian Noonan. I'm Senior R&D Engineer with the GCE, and I'll be your moderator for this session. Along with me, I have Cheryl Bukowski, who's the Professional Development Program Lead. Cheryl, thanks for helping out today.
Hi, everyone. Thanks for joining us.
Also, Benjamin Meyer. Benjamin's a software engineer for research and development with the GCE. Hi, Benjamin.
Hello, and thanks everyone for joining us here today.
And Allison Brucey, who is the GCE's program coordinator. Hello, Allison.
Hi, Jillian. Hi, everybody. Thank you for being here today.
All right, thank you, team. And now to introduce our panel of experts who have so generously devoted their time to this session today. So first we have Scott Silwick. Scott is Vice President with Colin Nicholas. He also serves as a lead technical advisor for the Fundamentals of Open Pit Slope Design course. Scott, great to see you today.
Hi, everybody. Happy to be here.
Next, we have Mark Rougier, who is Principal Geotechnical Engineer with WSP. Mark contributed a course module talking about, giving an introduction to data uncertainty. Mark, thanks for your contribution to the course, and thanks for being on our panel today.
Thank you. Glad to be here. Hi, everybody.
Also joining us today is Sam Timms, who is a senior consultant with SRK. And Sam gave us a module on dealing with data uncertainty. Sam, great to have you here. Thank you so much.
Thanks for having me.
Next up, we have Derek Kanakin. Derek is an engineering geologist with BGC Engineering. And Derek contributed a very interesting module on formulating target design acceptance criteria. Thank you so much, Derek, for being here.
Yeah, really happy to be here. Thanks for the invite.
Also joining us is Megan Gaida, who is Principal Geotechnical Engineer with Rio Tinto. And Megan's course module was on design requirements by project level. Thank you so much, Megan.
Thank you. I'm looking forward to today's conversations.
And lastly, but not leastly, we have Julia Potter. Julia is the Director of the Geotechnical Center of Excellence and is joining us on our expert panel today. Thanks, Julia, for contributing to the panel today.
Thanks, Jill. Thanks, everybody, for being here. Should be a great discussion.
All right, hopefully everyone is excited by those introductions and ready to submit questions and get involved in our discussion today. This is an interactive webinar, and the way that you can contribute your questions is to post them using the Q&A function, which you can find on the control panel of your Zoom. So if you click on the button that says Q&A, it should pop up a window. And within that window, you are able to type in your questions. You are able to see the questions that others have posted. If you really like a specific question and you'd like us to prioritize it, you can give it a thumbs up. We will see that. You are muted because this is a webinar and your video is off. So the way you communicate with us is through the Q&A or general conversation can go through the chat. We are recording this webinar and we'll be posting it to the course site and to the GCE's YouTube page when we're finished. And just a quick disclaimer that this webinar is intended for educational purposes only. And if you do need site-specific professional advice, we do recommend that you seek that out. All right, that is the end of our introductions, and we are ready to get into our question and answer session. So I will start this off. The way it will work is I'll read out a question, which will give the panel just a moment to consider their responses, and then we'll open up for discussion. And at this time, I'll welcome our participants to begin entering questions into the Q&A, and you can continue to enter them throughout the webinar. All right, so the first question, Mark, I'm going to direct this one to you to start. And the question is, considering the topic of data uncertainty, can you give an example of how you determine when you have reached a good enough balance of data or knowledge acquired to remaining uncertainty? And then also, what is this balance based on? Is it primarily limited by budget for site investigations, or what other considerations are taken into account? So I will invite Mark to start off with this, and then we can open up to the rest of the panel. Thank you, Mark.
Yeah, thank you for this question. I think there's a lot of different ways to look at this. I'll start with an example of where you have enough information. I'm picturing an open pit where we know there's a fault, and we all of a sudden realize that it could daylight in the pit, and it'll be a huge wall planar failure if it's really where it's supposed to be. So how would you know when it's good enough? And so you would keep drilling that fault until you'd hit it enough times in the area that matters that you're no longer surprised that you hit it where you thought you would, where your prognosis was. So that's one example. You have a prognosis for an outcome and you're reaching it. So in that case, what was the balance based on? It's based on having multiple points of confirmation of that fault. Is that limited by budget? Sometimes. Another one you asked is what other considerations can be taken into account? Sometimes say it's UCS, unconfined compressive strength data, and there are certain rules that, for statistical confidence, you might need 6 or 10 samples, or if the rock type is very variable, you could say, oh, for a pure statistical level of confidence, you might need 40 samples to show that, it doesn't matter how many more samples I take, my standard deviation or my coefficient of variation doesn't change. But there's another way to look at that too is, and if you're in a hard rock pit or something, and that's not very deep, you might not care that your UCS data is low confidence because the stability of your slope is insensitive to that strength. The strength is so good that that's not a control on design. So what is the balance based on in that case? It's based on the outcome of whether or not that parameters, you're sensitive to that parameter. And this will be my last elaboration. It could be you have a slope that's very sensitive to pore pressure. So how do you know you have enough balance is when your pore pressure data is matching your predictions. But in another slope may be insensitive to pore pressure. And so, then because it's not important to slope performance, that's where the balance is. I'll pass it to my colleagues to add to that, if anyone wants to.
Anyone else on the panel, please feel free to unmute.
Yeah,
Maybe Sam?
yeah. I just wanted to add, I mean, those are all good points from Mark. Some of this also goes into how aggressive or conservative your design is and what the risks or potential risks are based on what you understand about the rock mass or fabric or structures. And so, this is something that we get faced with all the time. You get a limited drilling program, right? And there's just a lot of uncertainty. So you end up constraining the design based on some of that uncertainty, taking more unfavorable material properties or anisotropy inputs to your models to try and manage that uncertainty a little bit. So more to the second question there.
Yeah, and that question of the balance really gets easier to answer once you start collecting more data. Basically, if you collect some data points and they all align the exact same and you're not seeing too much variability, then maybe you're feeling pretty good, like Mark said, with only 6 or 10 data points. But if you collect those 6 or 10 data points and you're seeing scatter all over the place, then that might be an indicator of, okay, well, maybe for this particular rock type or for this particular test, we need some more data, or we need to verify with an outside lab just to make sure that what we're seeing is real. Another question that we're asked a lot along this same line is, for a deposit for this level of study, how close do the drill holes need to be to collect enough data and have that confidence? And again, that kind of depends on how variable the data is going to be. So the answer to that question would be, how variable do we think the geology is? If it's a really variable deposit with a lot of changes happening rapidly in the geology, then we probably want to collect more data and have the data more closer spaced. If it's a more uniform deposit with uniform geology, maybe we can start out with having the drill holes a little further spaced apart. So there are a lot of things to think about to answer that question.
Maybe just one thing to add from my side, I don't know if we ever reach a specific target with any of these investigations or anywhere in our knowledge. It is a bit of a continuing journey. We're always improving things as we go. And I think the best projects are the ones that take that kind of view that, at every stage, I'm going to improve my knowledge. I'm going to improve my database. It never really stops. There's always something new to tackle when it comes to uncertainty in these designs. And we learn a lot as we go.
Any other comments from our panel here?
I would just add, and I think there were some really great examples. When you're thinking about the uncertainty in the design space, you might also think about what is your tolerable risk. Like, can you live with some bench scale failures, or can you live with some multi-bench failures? And that may dictate, how closely spaced your drilling needs to be and how much confidence you need. Is what is the scale of the problem that you're trying to manage?
And then just to show a relevant figure to that discussion. This comes from the course, and this is something we saw kind of repeated throughout the modules. And I think it's a good visualization showing that the relationship between data accuracy, how much data you have, increasing the relationship with how much uncertainty you have, increasing here, and then site investigation, expenditure, experience, increasing as you increase your data accuracy and reduce your data uncertainty. But as you can see here, there's always this area where you have your, as Mark said, I think this came from Mark, your presentation, correct?
That's right. Yeah. Irreducible variability.
Yes. Is there anything else you'd like to speak to on this slide before we move on to the next?
This is excellent. That's all.
All right, any final comments from the panel on this first question, or shall I pull up the next?
Yeah, just one other thing to think about on uncertainty with regard to this slide would be like model uncertainty or transformation uncertainty. And when I say model uncertainty, what I mean is that in rock mechanics and slope stability, our standard workflow normally involves using some empirical models. So an example of that might be the generalized Hook-Brown criterion for rock mass strength. And the point being there that if you had two rock masses that had the exact same UCS, MI, and GSI that were on opposite sides of the world, even though they had the same input parameters, the actual rock mass strength would be different in those two sites, just because of that transformation uncertainty using an empirical criteria. So whenever we apply empiricism to a design, that's another type of uncertainty to think about and to consider when we're looking at probability of failure and how accurate we're being with our analysis.
Thanks, Scott. All right, we do have one live question that's come in so far. So we're going through live questions and pre-submitted questions today. I'll remind our live participants you can submit your questions at any time throughout the webinar. So I'll pull up the first question that we have received, and I will address this to the entire panel. So if anyone would like to jump in, I would welcome you to volunteer on this question, which is, if I manage geotech drill campaign to enrich intact rock strength data per domain, how much variation and coefficient of how much coefficient of variance of UCS target should I pursue for each domain? I'm trying to figure that out here. So I think how much variance in UCS should be the target for each domain?
I'll take a first stab at what I think this question means. I think.
Please do, Mark. Thank you.
Tree, what you're asking is, when have I drilled enough? And that's why often in a geotech rock drilling campaign, there's a hierarchy of data. Every core run or part of a core run, there's a field estimated strength. And often in a drilling program, there's maybe systematic point load testing so that you can calibrate the field logger's estimated strength to that. And then you would have either UCS or other tests to correlate to that. And where you're going with that is at every level, like Scott was saying, it depends on the variability in your rock unit, lithological unit, or your domain. It could be that a coefficient of variation of 40% is as good as you can get. It's hard to know exactly. The only way you really know is to try. And if extra work doesn't seem to reduce your coefficient of variation, then that would be an argument not to do more UCS tests. You might do more just looking at the field R values that you collected or your point load test distribution to try to sort that out. Again, I'll pass it to my colleagues to build on that or argue with me.
Sure.
I really like what you said earlier too, Mark. Just maybe run the analysis, do a
Mhm.
sensitivity to UCS, run
Yes.
-1 and -2 standard deviation, and see how big of a
Yep.
difference it makes. If it makes a big difference, it pays
Mhm.
for more testing probably. If it doesn't make
Yeah.
a big difference, then maybe you're done.
Yeah, exactly. You may not care if
Yeah.
it's a hard rock pit and it's not very deep, or it's a moderate or a weak rock pit, but very shallow slopes for other reasons.
Hmm.
And you might be discovering something else about your underlying geotechnical model if you have a high coefficient of variation in your data.
Mhm.
You may have inadvertently stuck the wrong material together in the same domain, and maybe there's some further splitting or some further work to be done on your interpretation. So yeah, there's no simple answer as far as just targeting a COV value, unfortunately, in my experience.
If you were in a situation where the rock mass strength was your control, or the intact strength was your control, there is some guidance being published by Macchiota for what your COV targets might be for your overall confidence. How large a piece of that your UCS makes up, you would have to determine. For your specific project, it may be large, it may be small, but that is one mechanism to do those calculations if they're appropriate.
I think just adding on to what everybody's saying, it's always going to be high. Like the lab results that we see, they always come back with a high degree of variability, reflecting, changes in grain sizes and the crystal structure, or inherent anisotropy, or fractures, or microfractures, or veinlets. I mean, there's a lot of places where we can never get a single good UCS test, like porphyry deposits. So I don't think there should necessarily be a target in terms of the coefficient of variance, but really understanding your geological and alteration controls, the things that are actually potentially affecting the rock strength, becomes a lot more important. And then it probably just becomes that you're limited by samples, rather than trying to pursue a specific number.
Everyone. Thank you, Tree, for the question. Are there any final comments before we move on to another? I think our live group is getting warmed up now. We have a couple more questions that have come in. So I will pull up another of those. All right. I'll read this one out, give you guys time to consider, and then I'll open this up to the panel. This question comes from Meg, who's asking, we know there is innately a high degree of uncertainty within a geotechnical model, yet design acceptance criteria are often defined based on meeting a target factor of safety. This is particularly relied on when designing pit slopes for regulatory approval, here in British Columbia anyway. However, due to uncertainty, the factor of safety may misrepresent the actual stability condition and potential for actual pit slope failure. Do you foresee a change in the regulatory process that will allow pit slope designs to explicitly consider additional factors, for example, empirical data, performance, deformation modeling results, etc., rather than relying solely on a quantitative result? So I will open this up to the panel and I will look and see if anyone would like to volunteer to address this first.
Yeah, I can jump on this one. So just quickly, more in the tailings world, but at least in Alberta, performance-based design is part of the legislative body. So I think that is something that is something that the industry is trending towards, as opposed to strict factor of safety or probability of failure metrics. But really, for any kind of performance-based design, you need to have a slope there, and you need to have a lot of data. So you need something to be able to calibrate it to, and it really needs to be calibrated against itself rather than benchmarking against other projects. So it's always going to be a mix of things. But for special circumstances where you got things creeping or moving gradually and slowly over time, then yeah, it's either something that might need a regulatory change, or it's something that can certainly be applied for as variances with inspectors.
Yeah, and I think that's worth digging into a bit. You know, at least in my experience in BC, like I found regulators to be very hesitant to actually state specific factor of safety targets. We very much work on a professional reliance model, and they really want a professional to, you know, stand up and defend their design recommendations. How you defend it may be on the basis of factor of safety, but I certainly have used probability of failure in previous projects. So I'm not so sure if there's a regulatory change needed as much as maybe just professionals building more confidence in presenting their designs using these other criteria approaches.
I would add that in BC, beyond stability, there are prescriptive regulations on the size of the catch bench width to manage rockfall hazard. Most jurisdictions in the US and Canada under MSHA and other provinces like Ontario and Quebec don't have prescriptive catch bench widths. It's the onus is on the engineer to demonstrate that their catch bench width is in conformance. In BC, there's a regulation of minimum 8 meters width after back break, entirely to protect workers from rockfall. So that would be an example of a something beyond factor of safety that's already in there.
It's a good one, Mark. In fact, you're right. That is specifically laid out in the BC Mines Act. But I would be hard pressed to find anywhere where there is a mention of factor of safety specifically in the Act.
That's right. You do see often people go back to relying on guidelines for what is the consequence of failure for the slope. And you know, most pit slopes end up being around, it's the 1.5. I would say to a practitioner, if you're really uncertain, then you need to increase your factor of safety the way it's done in the guidelines for waste dumps, where if there's more uncertainty on the conditions, a higher factor of safety is applied. That might also help.
Yeah, and I think that's where these guidelines that the LOP has been working on have become so powerful over the years, because that's exactly what regulators have started to kind of fall back onto. I mean, I've had letters from regulators specifically citing the Reed and Stacy book. So it's you know, we're kind of the masters of our own domain, so to speak, as far as contributing to these guidelines and contributing to the direction of what the regulators end up doing.
Mm-hmm.
I just wanted to add that the performance-based design stuff becomes a lot more important at closure. You know, it's pretty hard to design or understand what's going to happen in 100 years or 500 years time to your slope. So that's sort of a natural evolution towards that performance-based design is managing closure aspects of these pits.
All right, thank you, everyone. Thank you, Megan. I see you posted that reference that was requested. I'm going to put that in the chat also. And just a note for our participants today, we are already halfway through the webinar. Time flies when you're having fun. But just to note, so Megan responded to one of our questions. You are able to see both open questions and answered questions, and our panel is able to type responses also to your questions. So just make sure you're keeping an eye on the Q&A if you might get a written response there as well. All right, that was a good discussion for Meg. Are there any final comments on this question before we move on to the next topic?
Yeah, I don't have the same experience as the rest of the panel, but certainly I've seen this to be very variable depending, you know, the jurisdiction in which you're operating. I think in the United States is the most maybe extreme version of the example where I think the guidance is just a safe and stable slope, and it's up to you to determine how to interpret that. So yeah, that versus the minimum 8-meter catch bench, I think are two ways that different governments might approach that.
All right, thank you, Megan. Thank you, Meg, for the great question. All right, so we have a few questions that are based around the topic of cost benefit analysis. So Derek Knacken, I know you talked about that in your presentation, so I'll probably first call on you to address this question I'm about to pull up. I'm going to quickly show a question that came in from the live group, but then move on to another question that's related, and I think they will kind of complement each other. So the live question is from Juan asking, how do you evaluate the cost benefit of improving slope design versus accepting a higher level of uncertainty? So maybe you can just briefly touch on that. And then the additional question specific to your presentation was this one here. You talked about the Ryan and Pryor reference for doing a cost benefit assessment. And you mentioned that some software may be available to assist with at least some portions of this. What software is that, and when do you use it in the process? And then, is the rest of the analysis manually completed, or are there any automated shortcuts for cost benefit design? So I think this is an open invitation to just sort of talk a bit about cost benefit design, and I will just remind you again of the first question, which is, how do you evaluate the cost benefit of improving slope design versus accepting a higher level of uncertainty? So Derek, I will let you loose on this one.
Okay, let's see what I can do. And I'm thankful that Scott joined us today so we can fill in the gaps on the tooling side. I guess the way I'm interpreting this question is when we talk about improving the slope design, I'm kind of interpreting that as improving the confidence in the slope design versus accepting a higher level of uncertainty, as opposed to, say, steepening a wall. But I think this goes back to the very first discussion we had in this session, which is, what is the cost of being wrong in your design? I think we already talked through a lot of really great examples, and I like Mark's example of, being in a hard rock pit with failure modes that are very structurally controlled. Do we really need a high level of certainty on intact strength in that particular example? Maybe not, but we might need a very high degree of certainty on our fault model, because those are the things that are going to really control the future performance of our slopes. So I think really, I come back to relying on my team of experts and my team of peers when I think about these kinds of evaluations. I don't see this approach, or I don't see this necessarily being an approach of a spreadsheet calculation, or looking back to a table in a book. I think this is a place where you really want to engage a team of experts, in your own organization, or maybe some external experts, to talk about, in an open way. Okay, well, what if we're wrong here with these parameters? What are going to be the impacts if the slope does become unstable? Can we handle that? And that team of people is going to need more than rock slope specialists around it. It's going to need mine planners. It's going to need the mine manager sometimes to have a really fruitful discussion about, can we manage the consequences of being wrong? So let's maybe talking around this one a little bit, but that's what kind of comes to mind.
And that's good, just to bring the discussion, so that's good. And Scott, did you have something you'd like to add to this, or to the other question that I showed?
Yeah, maybe we can just jump to the next question. I think Derek knocked that one out of the park.
There we go.
before Scott takes over, just to say, like, this one, a lot of consultants have developed some incredibly powerful tools, in-house tools that make these assessments, go smoothly. And unfortunately, most of them are just not commercially available. But they are available via those consulting firms who can help you answer these questions.
Yeah, that's right, Derek. The reference that was given Ryan and Pryor, exactly that InterAmp analysis software is an in-house software for C&I. But the exact same analysis can be done using, commercially available software as well. You could do the same thing with the Rock Science suite of software, because I know in there you can do a probabilistic slope analysis. And that's basically all the software is doing, is it's just considering different InterAmp slope angles, considering the variability in the structure and dip direction, strength, spacing, and length. It's basically varying all those parameters for a specific wall orientation and an InterAmp slope angle. And then what we're trying to get out of that is, number one, how many InterAmp failures do we expect on average for that slope configuration? And then how big will those InterAmp slope failures be? So whether you do that with an in-house software and external software, I think it can be done these days with either. The tough part with a cost-benefit design is it really involves a lot of different groups at the mine. It's not just a geotechnical exercise. To do the full cost-benefit analysis, we need to know what is the economic value of steepening that InterAmp slope angle. So how much NPV is there to be gained by that steepening? And then we also need to be able to assign a cost to those failures that we're predicting for different InterAmp slope angles. So we need to know the cost to clean up these failures, potential costs due to production delays, potential costs due to mitigation, and potential costs to have an expanded geotechnical team at the mine, expanded monitoring systems, whatever it may take to manage these potential failures and keep everybody at the mine safe. And essentially, once you have those two pieces of the equation, right, then we can just take the benefits, subtract out the costs, and usually when you plot those on a curve, you'll get a nice bell curve with an optimum InterAmp slope angle that would be the economic InterAmp slope angle. There's one final consideration with that optimized cost-benefit design, and it's, can it be mined safely? Just because it's the optimum cost-benefit design doesn't mean necessarily that it can be mined safely. That evaluation would need to be made separately based on the monitoring tools available, the pit design, and then the failure mechanism for the types of failures that are being analyzed. But yeah, so I think 20 years ago, it would be hard to do it without consultant software, but I think these days, I think there are enough tools out there available. You probably could do it on your own if you had to.
You could stitch it together with a smart mining engineer.
I think so.
Some good spreadsheet skills, yeah.
I think you could.
Yeah, I think that was a really good overview. I think one key takeaway, if you do make that cost benefit decision, is if the design team has accepted more risk in that equation, then the receiving mine team that's ultimately going to manage it, that stakeholder communication needs to be incredibly clear. That we have intentionally accepted some failures here, and we're expecting you to manage them so that they're not a surprise.
Which I think, Megan, a good thing to point out too is I think that's the case for most mines. I think almost every mine in the world is willing to try to economically optimize, monitor it, and accept that there will be some failures. Yeah. I think that's just kind of our baseline of where we're at today in the world.
Yeah, but if you get that disconnect between the design team and the implementation team, there can be some mismatch of expectations.
We've to do some of this type of cost benefit analysis, we've been pushing discussions with the technical services team and the implementation teams to, like, what is too big a failure? Like, what is it? Is it 6,000 meters cubed? Is it 1,500 tons? Like, what is it that you guys are going to stop work over, because that's when you do it? And it'd be good. Scott, you mentioned this too, and sort of Derek, you got to know that that's an input into this sort of exercise. It should be. What are they willing to accept too?
Yeah, absolutely. I mean, you don't want to get into a situation where the shuttle operator shows up for shift and says, "To hell with this. I'm not going into the pit because things are falling down around my ears," right? Like that totally gets in the way of what we're trying to accomplish. So, yeah.
Okay. We have another question that's similarly related. So we're going to continue this conversation on cost benefit analysis, but just kind of moving to the topic of timing. And maybe I'll call on Megan first for this since you presented on project stages. So Natalia's asking, does it make sense to do a cost benefit design at earlier stages of the project when we have more data uncertainty? I would think we needed more data to do this assessment. So is there a minimum stage of the project that would make sense to invest time on this? And then maybe also addressing the same question for a risk consequence design if the answer would be different.
Yeah, so this is a great question, and you want to do your level of effort proportional to your confidence, I think, when you work through the study stages. So at the conceptual level, you're really just looking for, is this a go or a no-go? You're not as concerned about optimizing the economics. And at pre-feasibility, you're assessing your options. So you're looking at a range of outcomes. You're not necessarily looking for the most optimized design. So I think until you really get to feasibility, you're more concerned with those bigger picture questions that we've been talking about, like, is there a fault that's going to cause a major problem? Is there something you can't live with, right, in this design? And then as you start to get into that feasibility and the detailed design and construction phases, that's where you can start tweaking those inner ramp angles with things like a cost benefit analysis. So that's probably my take on that answer. I'm curious to see if the panel has other perspectives.
I'm gonna add on to this one. So then this is actually what my last slopes paper was on, was early project stage optimization.
So we're going to get asked to have that put into the chat if you have that available, Sam.
Okay, I'll try and dig that up. Basically what it comes down to is talking to your friendly mining engineers and playing around with the slope angles and actually trying to get an understanding of how that's going to be impacting your tonnage, whether it's waste or total tonnage, and how that's going to affect the cash flow. And so at the early study stages, you don't want to be doing this on detailed design. You want to be doing this on optimization shells because they're relatively quick and easy to run. And this is where you can have a lot of variability in them. So these are good ways that you can get a really good and quick understanding of where your slope angles are actually changing. So if you've got a shallow dipping ore body or something, that footwall is always going to be at 30 degrees. Like, you don't need to be trying to optimize your inner ramp angles there to 65 degrees because it's always going to be 30 degrees. But the hanging wall where you got your high wall, that's going to be the one that'll be sensitive to changes in your design slope angle. And that can be something that you use to target your future geotechnical drilling or geotechnical investigations or numerical modeling or structural modeling, or whatever you're doing. So you can do stuff at an early study stage. You just don't want to invest a lot of time in it.
Yeah, I'm with Sam. I think there's value in doing an appropriate amount at those early study stages too. One thing that I see on some projects, work on a lot of porphyry projects, and in the footprint of your excavation can change depending on your assumptions. Your pit might get bigger, might get smaller. And so when you're planning things like near pit infrastructure, or you're planning or getting ahead of permit boundaries or permitting the footprint of your pit, like, I think it is really valuable to do some of these sensitivity analyses early on to test, how big your excavation might actually get at the end of the day. Yeah, I think there's a lot of value in that at these early stages too.
I think just adding on to that, Derek, one thing to understand is that most of the mining engineers, when they're running their optimizations, are taking your design slope angles and just adding 5%, 10%, 15%, and taking away 5%, 10%, 15%, without often realizing that that slope angle that you've given them is as steep as it's going to get. And they need to be going 5, 10, 15, 20, 30% shallower than the angles that they've been provided, and not pushing them equally, because it just tends to balance out the results and bell curve it around whatever design you give them. So you just need to be talking to the mining engineers as they're playing with the numbers that you give them.
Thank you, guys. Any final comments for Natalia? Thank you, Natalia. for the
I
great-
would,
Go ahead, Megan.
yeah, I see she's also asked about the risk consequence, and
Yes.
I think the overall takeaway from this discussion for me is, you might do all these things, these risk, cost, consequence, and cost benefit at all the stages, but the level of effort you put into them and the amount of time, that's what changes. So, we use these as a screening tool at the early stages. We get right in the weeds once we're up in the feasibility and the detailed design. But I think, yeah, looking at your sensitivity at every stage is a really critical step.
Thanks, Megan. All right, we have just over 10 minutes remaining in this webinar. I'm going to pull up another live question and we'll see what our panel thinks about this one from Samuel. So Samuel is stating that slope stability design is influenced by blasting explosive densities and powder factor, which really affects the stability of a slope. Discontinuities, minor faults, major faults, lithology, alterations, the inter-ramp angle, overall slope angle. How could we manage these variables to increase the factor of safety and decrease the probability of failure? So I don't believe I've come across anything related to blasting so far that's been presented in our current course, and I'm not sure if anyone here has knowledge on this subject. If you do, I would welcome you to comment on this question. And if you don't,
I could take a stab at this to start. So it's a good question, and I would want to split it into two. Is you're in a pit where the achievable bench face angle controls the inter-ramp angle and overall slope design, versus a pit where there's faults and rock mass failure such that the overall slope is insensitive to the bench face angle. An example might be a weaker rock, copper porphyry or something with an inter-ramp angle or overall slope angle in the 40s, where the reasons for that overall slope angle are all of the problems, versus say a hard rock pit, where if you could consistently get an 80-degree batter angle or bench face angle, you could steepen your slope up. So, and this also leads to the types of controlled blasting and perimeter wall blasting that you're doing. If you have pre-shear or pre-split blasting and you have favorable rock, you can do some incredible things and get some very steep slopes. Whereas in different materials, doing a pre-shear is a waste of time. Often in some, say at feasibility level slope designs, if it's a good rock mass, not a lot of fractures in it, we will assume we can get a 75-degree bench face angle with a vertical pre-split, or sometimes an inclined. But if I know that we're only doing trim blasting or cushion blasting on the wall control, then even without checking the continuity, the discontinuities or the fabric, I'm already in a space where I'm never going to get better than 65 to 70 degrees on my bench face angle. And then I'll go in, and often that's a discussion with the mine team, is what kind of blasting are you going to do for your walls? If it's a big iron ore mine, they may never do a pre-shear because it's just not worth it. And then, if you only have pit slopes that are production blasted, the final walls, then I wouldn't expect to get a bench face angle better than 55 degrees or 60. What you'll notice in a lot of pit shells is a very common face angle in a pit shell is 68 degrees or 65 or 70. Where does that come from? Like, that's often the dig angle of a bench that's been moderately blast damaged and was trim blasted or cushion blasted. So I think it's somewhat considered in there. You've got to do that at the planning stage. It would be on us as geotech engineers to recommend what kind of blasting we think is suitable for the faces. But for something like major faults, if they're into ramp scale or something, that's beyond blasting. If you're controlling for those, it might not have anything to do with blasting.
Thanks, Mark, for attacking that one. Any comments for Samuel? We do have, I'll let everyone know that we are currently developing a course on geotechnical considerations for blasting. That's going to be the newest GCE course that we are aiming to put out this coming fall. So I don't know much about blasting at this point, but I soon will be an expert after helping develop that course.
I just wanted to add on to Mark's points. I think all his points are totally valid. Blasting's not really an IRA or OSA problem. It's your benches, and getting control of your benches lets you steepen things up, but it's not really affecting your overall stability. If you want to improve your blasting, it comes down to trial and error, experimentation, QA/QC, and recording what you're doing and what you're doing differently. And so I think that's the one thing that's missing from a lot of sites is actually recording what the powder factors you were using, what the spacing was, what the delays were, how you were orienting that initiation line against your face, and then reviewing that with that actual wall performance. So if you want to tidy up your blasting and improve your blasting, that's what it comes down to, is making sure that everything's well monitored, well recorded, and that you can actually go back and look at what you were doing and what you were changing. And all the preparation stuff goes into it too, right? It's not just explosive densities and powder factors. It's hole condition. It's making sure that your floors are level and holes are evenly spaced and even depths and everything like that. So.
Yeah, Sam, you're absolutely right. It can go even further than that. If the holes are uneven depth, and then the next level of the pit is being drilled through deeper blast damage, and then there's more cratering, and the problems stack and stack. And then the drillers might be intentionally drilling deeper because their holes are collapsing. And so in order to get to the right depth, they drill deeper to catch the collapse. There's a whole cycle of things that could be going on that you or the people on site have no idea, or they're not very much paying attention to until a lot of bad habits are established, or just habits, because nobody's been measuring it.
Yeah, we didn't even touch on water, but if all
yes, water and blast holes.
And then you get a whole different range of outcomes. So.
Mm-hmm.
All right, thank you, Sam and Mark. I think we have time for just one more question. And there was one that came in pre-submitted. We have completed all our live questions. Thank you, live group, for those questions. I thought this question was interesting and might just be a good talking us out of the webinar conversation. So it's a broad question, and it was directed at Derek. So it was to something related with your presentation. The question is, considering that the reliability of any slope design is a function of the underlying reliability of the models that support it, and the popular saying that, quote, all models are wrong, but some are useful, how do we then reconcile that our design is reliable if our models are wrong?
a great question. It's just the perfect mix of of cuteness in that question. You know, I think saying the models are wrong is probably a little bit of an overstatement, and we know it's meant to kind of provoke a response. That's why we use that word in this quote. You know, they're models. They're not perfectly accurate representations of reality. That's really what models are. We all know that. So are they wrong in that way? I guess, but you know, I think put that aside and just you know, accept that they're not as accurate as they could be. But that's part of what our job is to work on making the models more accurate as we can get them, and then you know, dealing with the final remaining what was Mark's term there, the remaining uncertainty that we have in all these models. And we talk a lot about the geotechnical models, but let's not forget that when we talk about models, we're also talking about the calculations that we're doing, our wedge calculation, our planar sliding calculation. These are all models with all kinds of assumptions made about the physics that go into the math. So we can make useful, reliable engineering decisions based on these imperfect models because we back them up with experience and, you know, logical thinking and tried and true approaches. You know, fortunately, our designs are not simply a function of our models.
Fantastic answer. Mark, I saw you unmuted.
I was just going to add to what Garrick said is the relying on experience. Another word for that is benchmarking. If there's an analogous pit or an analogous pit wall somewhere that we can share, and that will help with confidence too. It's a calibration to another site.
Yeah, I think both those thoughts are really good. I was just going to share my personal experience and how it applies to this question. You know, some of the models that I've seen that, you know, kind of miss the big picture or resulted in an issue. So something for a model that you know, necessarily wouldn't call reliable. It's not because the coefficient of variation of the UCS was too small, right? It wasn't because there were 10 samples instead of 20 samples that the model didn't work and didn't predict reality. It was more something like a rock type was missed in the geologic model. So there was high geological uncertainty and something was missed there. Or there was a zone in the pit that had very high pore pressures and there wasn't any piezometer data in that part of the pit. And so that part of the model was missing. So when checking, is my model reliable for this instance, it's always good just to take a big step back, look at the big 180 picture, look at the deposit, look at the geology, look at all the data feeding the model, and then see if there's any big pieces that might be missing.
Sam?
I think that you can just decide if your models are reliable, your design's reliable, as if your models are representing a credible failure mode and you've applied an appropriate sensitivity on your inputs. After that, you're sort of stuck to the limits of your geological knowledge, right? So if you don't know a fault's there, you're not going to be putting it in your model. So.
And Megan, if you like, I give you the last word here.
They were all awesome answers. Yeah, I think it comes back to that conceptual model piece. And like Scott said, it's the big picture stuff, right? We can test sensitivities if we've identified and understood the big picture controls. It comes down to our geological understanding and our concept of the pit that we're working in.
All right. That was a great question and really wonderful responses from all of you. We are out of time for our webinar today, and I just want to make sure I say thank you so much to our panel of experts that were here today. We really appreciate your time today, as do our participants. It's so invaluable to be able to have these types of discussions, and we really appreciate you very, very much. To our panelists, thank you for joining us today. We do have another webinar coming up on April 22nd, which is going to be on performance monitoring and design implementation with another panel of experts. So please join us for that. Check out LinkedIn and you'll see the announcement there. And then if you are interested in the course, I'll just leave this up for a few minutes so that you can go ahead and check that out if you're interested. So thank you, everybody. Have a wonderful day, and we'll see you next time.